Hello everyone, welcome to our channel Mathematics Pathshala. This is a problem of CSIR NET December 2023 Mathematical Sciences. This is a question from complex analysis. Let us first read the question. Let x be an uncountable subset of C and f such that C to C be an entire function. Assume that for every z belongs to x, there exists an integer n greater than or equal to 1 such that fn z equal to 0, that is nth derivative of f at z, which is 0. Which of the following statements are necessarily true? Option 1 says that f is identically 0. Option 2 says that f is a constant function. Option 3 says that there exists a compact subset k of C such that f inverse k is not compact. Option 4 says that f is a polynomial. So one by one we will discuss the options. First, see, if we simply take this uncountable set x equal to C, the whole complex plane, and if we take simply f equal to the identity mapping I, that is fz equal to z. So then clearly we have our f dash z equal to 1 for all z, and also f double dash z equal to 0, that is this is f2z, this is equal to 0. So we can conclude that for all z belongs to x, this n equal to 2 such that f to z equal to 0, that is the given condition of the question, is satisfied. Now see, for option 1, f is 0, here f is not identically 0, f is identity map. So option 1 is not true in general. For option 2, f is a constant function, clearly identity map is not a constant map. So option 2 is not true in general. For option 3, clearly if we take any compact set k, then as f is the identity map, so our f inverse k will be also equal to k, which is compact. So for every compact set k, f inverse k must be compact. So option 3 is not true in general. So it is clear that option 4 must be true, but here we will prove that if this condition is satisfied, then f must be a polynomial. So for this, we need some important theorems in complex analysis. See first, as f is entire function, so f is analytic at every point of C. So in the neighborhood of 0, we can have a Taylor's expansion of f, and that is of the form like fz equal to summation a n z to the power n equal to from 0 to infinity. Now just okay, so we are given that this condition that for every z belongs to x, there exists an integer n such that f and z equal to 0. Actually we claim that we will first prove that there exists this statement. We now try to prove that there exists an n belongs to n such that this fn z equal to 0 for all z belongs to C. This statement only we need to prove that, because if we can prove this, then easily from this statement we can prove that f is a polynomial. Simply repeated times of integrating this, we get first f n minus 1 z equal to a constant function, then f n minus 2 z equal to f n minus 2 z is a polynomial of degree 1, and continuing this process ultimately we get f is a polynomial. So we need only to prove this result. So for this, if possible, let this thing does not happen. So that means there does not exist such n such that f and z is identically 0. That means actually for every n belongs to n, this f and z, that means f dash z, uh, f double dash z and so on, all are not identically 0. Here simply consider this function the product of all such f and z, n equal to 0 to infinity. Clearly when n equal to 0, then this is actually fz. So consider this function. So we will have assumed that f is also not identically 0, because f is identically 0, then this is also a polynomial, 0 polynomial. So that will be then the 4 will be true. So we assume that f is not identically 0, and then consider this product of such f and z. Now see, clearly all such f and z are entire function. As f is entire, so all such f and z are entire. All such f and z are entire. And hence, there is a result that an entire function cannot have uncountable number of zeros. An entire function cannot have uncountable number zeros. This result also we now prove. If possible, suppose an entire function, say h, has uncountable number zeros. So that means 8z equal to 0 for all z belongs to set, say k, and k is uncountable set. Clearly, any uncountable set in complex number has a limit point. That can be proved easily. We are not going to prove this result, that any uncountable set, just we are stating this result. Any uncountable subset, any uncountable subset of C must have a limit point. So this result, we are not going to prove this. Very in a easy way we can prove this result. So as now we are going to show that an entire function cannot have uncountable number of zeros. So if possible, suppose h is an entire function which has uncountable number of zeros. That means hz equal to 0 for all z belongs to k, where k is an uncountable set. Now as this k has a limit point, so k has a limit point in C, so we can conclude that hz equal to 0 for all z belongs to C. That means h is identically 0. So this why we can say this? This is we can say by interior uniqueness theory. This is a famous theorem in complex analysis, interior uniqueness theorem. Interior uniqueness theorem says that if two functions coincides on a set having a limit point in a domain, then these two functions coincide with the whole domain. So here the domain is complex plane C, and K is that uncountable set which has a limit point. So as this 0 function and h function coincides on K which has a limit point, so this function h and 0 function will coincide on whole complex plane. That means hz equal to 0 for all z belongs to C. So h will be identically 0. So this statement should be some a modified form, that an non-zero entire function. So entire, if a entire function is 0, then this must have all all complex numbers are the zeros of this function. So the statement should be a non-zero entire function uh, non-zero entire function cannot have cannot have uncountable number of zeros. So now this is we have an result that every entire function which is non-zero cannot have uncountable number of zeros. Now look at this function gz. Now see, we have assumed that all such f and z are non-zero, because if some f and z is 0 for some n, then our result is already established. So we assume that all such f and z are non-zero. So now this all such f and z are entire and non-zero, and as entire, so all they have countable number of zeros. All they have countable number of zeros. So we can assume that this fz, the set of zeros of f, is denoted by a0. The set of all zeros of f1 is denoted by a1, and so on. The set of all zeros of fn is denoted by an. So clearly this union I equal to 0 to infinity ai, this will be the set of all zeros of g. This will be the set of all zeros of g. Now see, just proved we have now that an entire function cannot have uncountable number of zeros. So all such AIs are countable. So all such AIs are countable, and hence countable union of countable set is also countable. So this A equal to this also is countable, and which is the set of zeros of G. So what we get? We get that the set of all and clearly this union is the set of all zeros of G. So we have, and clearly this is precisely the set of all zeros of G, because if there is any other zero of G, then that zero must be in one such AI. So now we have Gz equal to 0 for all Z belongs to A, where A is a countable set. So what we get? The set of all zeros of G is countable. Now see, we are given that for all Z belongs to X, there exists N belongs to N, such that this Fn Z equal to 0. That means this for all such Z belongs to X, Z is a 0, Z is a 0 of this Fn for some n. That means this Z belongs to this An. So we have for all such Z belongs to X, Z belongs to some An for some n. So we have X is subset of this union An, n equal to 1 to up to 0 to up to infinity. This right hand side is a countable set, but left hand side is uncountable set by our hypothesis that X is an uncountable set, which is a contradiction. This cannot happen. So this cannot happen. So where we get this contradiction? Because we have assumed that this thing, we have assumed that for all n belongs to n, f and z is not 0. So we must have, there exists some n such that this thing, such that f and z equal to 0 for all z belongs to C. So now by repeated times of using integration, we can prove that f is a polynomial, because this fn minus 1 z will be a constant, say C, then fn minus 2 z will be this cz plus some constants, say this is, we can write C0. So this is C0z plus C1, and similarly up to this fz equal to, we have something z to the power something plus sorry, this C0, some constant z to the power something plus some constant z to the power something plus dot dot up to some constant. So this is a polynomial f. So in this way we can prove this result. So f is a polynomial. So here option 1, 2, 3 are not the correct options, and option 4 is the only correct option. Thanks.